We're going to be looking at Boolean Algebra and Logic. So, Boolean Algebra and Logic uses essentially the binary states that we've looked at. So you've got either on or you've got off. You might have true or you might have false. You might have 1 or you might have 0. So those are the different conditions that we often look at. Okay, so for us to start off with this, we're going to be starting looking at what's known as logic gates, and we're going to be identifying how they sort of operate, and then once we've gone through that, we'll be able to look at more examples of how to convert between different things that you are given and find a solution for the other things that you might need. You'll see later on as we go through that. Okay, so the first gate we're going to be looking at is the NOT gate. Okay, so consider this circuit diagram. So you've got your battery that's going up through some resistor called R. That's going down, it's going through some globe, and from there it goes back to the battery. Okay, and what we're going to do is we're going to be placing a switch over this globe. Alright, so the switch we're going to be calling A, and the globe we're going to call Z, or Z, depending on where in the world you are. Okay, so if we have a look at the conditions and put into a table. Okay, so we've got A, which is the switch, and we've got Z. So what we're going to do is for A, we're going to look at all possibilities. A is going to be off, or A is going to be on. A is going to be deactivated, or A is going to be activated. So if the switch is not activated, so it's open, what's going to happen to the light bulb? Will the light bulb go on or not? It will go on. So therefore, Z is equal to 1. Okay, now what should happen if we should close that switch? Well, current will come around. It will not want to go through the light bulb because there's some resistance over there. It will either come through the switch. It's going to take the path of the least resistance. Okay, so as soon as the switch is closed, that means that there's going to be a short over the light bulb, which means the light bulb's not going to come on. Okay, so therefore, Z, or the light bulb, or the output, would be 0. So as you can see, the output Z or Z is it's the inversion of the input A. Okay, so this is what's known as the truth table for the NOT gate, and the diagram for the NOT gate is represented as the following. So you've got your input A. In NOT gates, it's only got one input. This symbol you might have come across before. That's known as a buffer. So whatever comes in goes out. There's a little circle over there, and that circle represents the NOT, the inverted value. And then you've got the output Z. Okay, so that symbol is something we're going to be using when we do circuit diagrams for these logic systems. The expression is often referred to as Z is equal to A naught, and that's given with a little apostrophe. Now there are some textbooks out there and some systems that would go and say that you can also write Z is equal to A and then a bar over it. And I'm going to advise you not to use that notation. The reason being is that especially if you've got large expressions and you've got a whole bunch of expressions that are not in, you end up having this lengthy expression with a whole bunch of bars on top of it or lines above it, which just becomes really messy and difficult to follow. And there's also chances of making errors. So my advice is don't use this type of notation, use this notation rather. It's easier to do. It's also less ink that you use. Okay. So that was a NOT gate. Let's have a look at another gate. The next gate we're going to be looking at is the AND gate. Okay, so again, we're going to be looking at the circuit diagram. Let's consider a circuit. So you've got your battery going up. You've got two switches, switch A, switch B, and from there we're going down to a globe, which will then go back to the battery. Okay, so now that we've got two switches, we've got two inputs. The user can give two inputs. Okay, so therefore we're going to have a truth table that will have A, B, and Z. Okay, now depending on the number of inputs, it basically comes down to the different options are 2 to the power of n. So we've got two inputs, so it's 2 to the power of 2 is 4 different options are available. And essentially we're going to be counting in binary. I know that a lot of people would go and find some pattern, or they'll try and write things down. My advice is always count from 0 and onwards up to the end, because the value 0 is often forgotten in the truth tables, and also it allows us to make sure that we look at all possibilities. Okay, so if we had to count from 0 and looking at 2 bits for all numbers that's got 2 bits, you start off with 0, 0. That would be representing your 0. Next number is 1, which is 0, 1. The next number is 2, which is 1, 0. And then it's 3, which is 1, 1. Okay, so here we have to look at this. If switch A is not activated and switch B is not activated, will this light bulb Z go on? No, it won't. If switch A is not activated but switch B is activated, will this light bulb go on? No, it won't. If A is activated and switched on but B is not, will the light bulb go on? No, it won't. If both switches are activated, will the light bulb go on? Yes, it will. Okay, so it's only when both inputs or all the inputs are equal to 1 that it will be giving an output of 1. Now we could have another switch over here in series and call it C, and the same will apply. So we could have A, B, C, and our output Z. Okay, and now that we've got 3 inputs, 2 to the power of 3 is equal to 8. So we've got 8 different inputs that we can consider. Okay, so we can draw our table like such. And it's a good thing if you've got lines going across your page or so, because then it allows you to keep track that you don't get confused between the different values. Okay, so now that we've got that, let's look at all the inputs. So again, we're going to count from 0 using 3 bits. So it's going to be 0, 0, 0. 0, 0, 1 is 1. 2 is 0, 1, 0. 3 is 0, 1, 1. 4 is 1, 0, 0. 5 is 1, 0, 1. 6 is 1, 1, 0. And 7 is 1, 1, 1. Okay, so that's all the inputs that we are now considering. Again, if any of the inputs are 0, it means that your lights are going to go on. So we can even look at A, and because A is all of the inputs up to this point is 0, we know that the output will be equal to 0. We don't even need to worry about looking at B and C. Again, if we look over here, B's got 2 zeros over there. Even though A's might be 1s and might be activated, B is 2 zeros. So we know that for those two conditions, those outputs are 0. Over here we've got C that's a 0. So even A and B is equal to 1. It still won't switch on. So we can make that a 0. It's only when all the inputs are equal to 1, then only will the output be equal to 1. Okay, the symbol to represent an AND gate, it's a straight line, and it's got half an arc type of shape. You've got your inputs on this side on a straight line, which might be A and B, and you've got your output Z over there. The expression for this is Z is equal to A dot B. So the dot is like a period, like your multiplication that you would use for your math notation. And you'll see later on, we actually don't even have to write that dot always. If the characters are next to each other, we can assume, as we do in math, we can assume there's the period in between the characters, and we can, so that would be equal to, for example, just AB. Okay. What should happen if we should have 3 inputs like we did for this truth table? Well, the same thing happens. We've got our gate, and we've got 3 inputs. So that's A, B, and C, and our output Z. Again, your expression for this would now be Z is equal to A, B, C. Okay, so all the other gates we'll be looking at as well later on. We might only use 2 inputs. Sometimes we might look at 3 inputs just to sort of have a look at the possibilities. But it doesn't matter how many inputs you can have. You can have 100 inputs over there, and the same principle will apply. The same truth table will be implemented. The same conditions will be looked at to make sure that all, well, for the AND gate at least, that all the inputs must be equal to 1 for the output to be equal to 1. Okay, so let's have a look at the next gate, which is the OR gate. Okay. Now the OR gate, you can sort of consider it as a circuit diagram in the following fashion. So we've got our battery, which goes up, and then we're going to have a switch over there, but parallel to that we're going to have another switch, and parallel to that we're going to have another switch. So in this case we've got 3 switches that are parallel to each other. So that's going to be A, B, and C. And then we're going to go through our light bulb, which will then go back to the battery. Okay. So in this case, if we have to look at the truth table, we can have A and B and C as well, because we've got now 3 switches, 3 inputs. Okay, and we've got our output Z. So let's have a look at all the different inputs you can have. So that would be 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. The other reason that I'm putting the emphasis in terms of counting from 0 all the way up to 7, or from 0 up to the final number, is that we find that, especially if this should be something that you've got to mark and identify what is happening, a lot of people would go and write all the numbers, and they'll have all the possibilities, but it will be all juggled up. So in other words, you might have 0, 0, 0 right at the end. When you're marking many scripts, you try and just sort of see if the pattern of the output is correct, and if that's correct you give the marks. But often it is that there is a chance that we might not see that the 0, 0, 0 is at the end, and therefore might mark it incorrect. So keep in mind that it's always best to write it from 0 up to 1, 1, 1. Okay, so with the OR gate, if we had to switch on switch A, or let's look at this. If switch A, B, and C were switched off, what would be the output? Well, the light won't go on, so we'll have a 0 over there. If we had switch A switched off, switch B switched off, but switch C might be switched on, would the light bulb go on? Yes, it will. Same case if only switch B is switched on, would the light bulb go on? Yes, it will. If switch B and C were switched on, but switch A is switched off, would the light bulb go on? Yes, it will. And can you see that it doesn't matter, as long as one of the switches are activated, the light bulb will go on. So we can see that A is 1 over there. As a matter of fact, it's A is 1 for all of the remaining ones. Final one, we've got A, B, and C that's activated, which means the light bulb will go on. Okay, so with the OR gate, it's essentially if any of the inputs are 1, the output would be 1. And obviously, you can also just have this represented as for 2 inputs, if you should have only 2 switches, which will be 4 inputs. That would be 0, 0, 0, 1, 1, 0, 1, 1. So that would be 0, 1, 1, 1. Okay. The symbol for the OR gate, it's a curve back that you've got over here, and then it looks almost like the wing of a like a jet plane. These stealth planes curves up to a point in the front. Okay, this would be your output, which would be Z, and then you've got your inputs A and B. Again, if there was C as well, you'd have an input C as over there. It's very important to note that this back is not just a straight line. It's a common mistake that people make. The expression for this would be Z is equal to A, and in all operators represented with the plus sign, so A plus B. Again, if you've got 3 inputs over there, you could represent it as Z is equal to A plus B plus C. Okay, so that's the basic concept behind the OR gate. It's just important to take note that the symbol for the OR gate is a lot different compared to the AND gate. Okay, so those were the 3 basic symbols or gates that you often come across. Let's have a look at another one. Now this is a little bit more of an advanced gate, which is known as the NAND gate. And the NAND gate stands for not AND. Okay, so having a look at that, it's essentially the symbol for the NAND gate is represented in terms of, you've got your normal AND gate, you've got your normal inputs A and B, or you could have more if you wish to, but there's a little circle at the output. And if you remember with the NOT gate, you had a little circle that indicated it was a NOT. So that would indicate it's a NOT, and that would be your output Z. You could also have represented this as A, B as your inputs, go into an AND gate, which then goes from there to a NOT gate, which goes to your output Z. The thing is though, now it's 2 components that you've got to use, and often you're able to get components that have got these gates already built into them with the NOT operator in it. So instead of having to get now another component that's for the NOT operator and then another component for the AND operator, you're able to get one that represents that. Okay, the NAND gate has got a truth table A and B, output Z, and again we're going to be looking at 0, 0, 0, 1, 1, 0, 1, 1. Again, you could have 3 as well, if you 3 inputs if you should, or even more inputs. Okay, so A and B, which would give you normally a 0, okay, but it's not it, so therefore the output is 1. If we looked at A and B, and A was 0, B was 1, that will give you an output of 0, but it's not it, so it becomes 1. Okay, now we're going to be looking at A being 1 B going to be 0. If you add those two together, they're going to be 0. Now we knot it, which makes it 1. And if A is 1 and B is 1, if we had to add them together, you'll get an output of 1. Going through a NOT gate will give you an output of 0. Okay, so essentially it's the inverted of the AND gate. So again, all of the outputs would generally be equal to 1 unless both or all the inputs are equal to 1. Then the output would be equal to 0. The way we'll express this is Z is equal to A, B, and the whole expression we're going to put in brackets, and we'll put an apostrophe over there to represent the NOT. Okay, so you might have guessed. What about for OR gates? Is there OR NOT? Yes, there is. And that is known as the NOR gate. So that is not OR. Okay, again, the NOR gate looks very much like your OR gate. So you've got your bow at the back going across to a point in a semi-arc fashion over there. You've got your inputs A and B, or more inputs if you wish. But you've got over here a little circle which represents a NOT before it goes to the output Z. The truth table for your NOR gate is, so we'll have A, B, and Z. Again, we'll be looking at all the numbers, so 0, 0, 0, 1, 1, 0, and 1, 1. So that's our different inputs we're able to get. Okay, so if we looked at just the OR part of it, A or B is equal, if both were equal to 0, you get an output of 0. But now it's knotted, which gives you an output of 1. Remember, with OR gate, if any of the inputs were 1, then the output would be 1. Okay, so if we've got A, which is a 0, and B is a 1, if we add those two together, the output would be 1. But now it goes to a NOT, so it becomes a 0. And similarly, with all these other ones, because there is one of them that's equal to 1, one of the inputs are equal to 1, the output of the normal OR gate would be equal to 1, knotted would give an output of 0. The expression that we have for the NOR gate can be given as Z is equal to A plus B, or A or B, and then or in bracket NOT. Again, if you've got an input C, it would be just A plus B plus C, or in a bracket, and that's all knotted with this apostrophe. Okay. Now there's one more gate that we're going to be looking at, which is something that's a little bit different to what you might have seen in the past. Okay, and that is known as the XOR, or also maybe pronounced as the XOR gate, and it's essentially this stands for exclusive OR. That is what the XOR gate stands for. Okay, so the symbol for the XOR gate, well, there's a circuit diagram involved for this as well, but it gets very complicated, very confusing, so I'm not even going to go into that. But the symbol for the XOR gate is, again, you've got, as you've got for your OR gate, you've got your curve back, which then goes out towards a point. But with the XOR gate, we've got another curve at the back. Okay, so it's like a double curve at the back. Then we've got our inputs, which will be A, B, and C. And then we've got our output, Z. Okay. The truth table. Now for this one, I'll actually go and do 3 different inputs. And same thing applies, and you'll see there's a pattern that we've got to take into account. So we've got A, B, C, and output Z. Okay. So we do our table, and we're going to be looking at all the possible inputs that there are. So there's 0, 0, 0, 0, 0, 1, 2 would be 0, 1, 0, 3 would be 0, 1, 1, 4 is 1, 0, 0, 5 is 1, 0, 1, 6 is 1, 1, 0, 7 is 1, 1, 1. Okay. Now, with the XOR gate, it's essentially a situation where if there's only 1, 1, the output would be 1. Okay. So we can look at this and say, well, that's quite easy. There's only 1 over there. 0, 1, 0 would give you an output of 1. 0, 1, 1. Okay, that's not a situation. Over here we've got a situation of 1, 0, 0. So that's got only one input of 1. So we can place a 1 over there. But what happens if, yes, and then we've got, if all the inputs are 0, then the output would be 0. But what would happen in a situation where we've got, for example, 2 inputs that are 1? And if there's 2 inputs that are equal to 1, that would be an output of 0. Similarly, we've got over here 2 inputs that are 1, so that would give an output of 0. We've got 2 inputs over here that are 1s, which gives an output of 0. Okay, but if there's 3 inputs that are 1, then the output would be 1. Now have a look at this. This is something that you've actually come across in your binary notation with the addition of binary numbers. If you had to say 0 plus 0 plus 0, that's obviously equal to 0. If you had to say 0 plus 0 plus 1 is equal to 1. 0 plus 1 plus 0 is equal to 1. 0 plus 1 plus 1 is equal to, what's that equal to? It's equal to 0, carry over 1. Okay. 1 plus 0 plus 0 is equal to 1. 1 plus 0 plus 1 is equal to 0, carry 1. 1 plus 1 plus 0 is equal to 0, carry 1. 1 plus 1 plus 1 is equal to 1, carry 1. So even though we're not actually putting down the carry over value of that carry over 1 though, it is whenever there is an odd number of 1s, the output would be 1. If there's an even number of 1s, the output would be 0. Or if all the inputs are 0, then the output would be 0. Okay, so essentially when you do an addition on a computer, the computer's actually got one of these XOR gates in it that actually then does the calculation and to determine what the output is. Okay, so the expression for an XOR gate would be Z is equal to A, and the symbol for XOR is the normal plus sign as you would for OR, but it's got a circle going around it. So A XOR B XOR C. Okay, so we've basically looked at the different gates that there are. Now, essentially, there's 3 different conditions or 3 things that you could be given, and you've got to find the other 2. So, for example, I could give you some logic diagram, and I could ask you, okay, find the truth table or find the expression. Or I could give you a truth table and ask you to find the logic diagram and the expression. Or I could go and I could ask you to find, I could give you the expression and I could ask you to draw the logic diagram or give the truth table. So those are the 3 different scenarios that you can have. Okay, so now that we've looked at all the different gates that are out there and that's possible, let's look at an example. Okay, so essentially you're going to be given the following. Okay, so there's going to be some circuit diagram, some logic diagram that we're going to be looking at. You've got inputs A, B, and C. Okay, and A might be going through a NOT gate as such. C might be going through a NOT gate, as such. A naught will come out, maybe might get ANDed together. Okay. Then we might have, say, okay, well, you know what? What I want to do is I want to have this C naught ANDed, or no, let's make it ORed with the output of that gate over there. Okay, so we OR that together as such. Then we're going to take this output and we're going to put it through an AND gate. I'm going to AND that with A. So I'm going to tap off from A over there, bring it across, and have that as an input to this gate. Okay, that should be a straight line over there. And then I'm going to take this output over here, and I want that to be going through an XOR gate. Okay, and that's going to be XORed with C. So we're going to tap off from C over here and bring it across. Okay, and then this output I'm going to put through a, let's make it a NOR gate as such. So we've got our 0 over there, it goes to a Z over there, and our other input will also be A. I'll tap off from there and make it come across over there. So as you can see, it's like a circuit diagram we're essentially drawing. Okay, so let's say you are given that. Now you've got to find the truth table, and you've got to find the expression. Okay, so let's start off with the truth table. We've got A, we've got B, and we've got C. Those are the inputs. We could have more inputs, but those are the ones that we're going to be looking at. Okay, so because we've got 3 inputs, we've got essentially 8 different possibilities. Okay, so we draw our table like such, and we're going to be looking at all the inputs. So I'm just going to draw the line going across over there for the headings. Okay, so let's look at all the inputs. So we've got 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. Okay. 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Okay. Alright, so let's have a look at things first. Let's have a look at, if we look over here, we've got A going through A naught. Okay, so I'm going to be looking at what is A naught. And I'm going to have a column specifically for that. Okay, so A naught is whatever's A is inverted. Okay, so A is a 0 over there, so it would be a 1. A is a 0 over there, so that would be a 1. A is a 0 over there, so that would be a 1. And A is a 0, that would be a 1. And then these 4 ones over here would all be zeros. Okay. So we've taken into account this NOT gate over there. Okay, the next thing I'm going to be looking at is this output over here. So that A naught goes as an input and gets ANDed with B. So I'm going to call this output over here P. Okay. Now, so I'm going to, essentially what I'm going to do is every output from each gate, I'm going to label that. So that's going to be P. The output of this gate will be Q. The output of this gate over here I'm going to call R. And the output of this gate is going to be S. The output over here of this gate is obviously the final output. Okay, so I'm going to have P over there. So now that we've got P is equal to A naught and B. Okay, so if we look at A naught and B over here in each of these two columns, so B, which is 0, ANDed with 1, gives you an output of 0. A is 0 over there, A naught is 1, ANDed together gives you an output of 0. And B is over here 1, A naught is 1, and those together, they equal to 1. So keep in mind with the AND gate, both inputs need to be 1 for the output to be 1. So I can go through this list, these two columns quickly, and see, well, there's 2 1s over there, and there's no other scenario that we've got both B and A naught that are equal to 1. So that would mean that all the other outputs for this specific gate would be equal to 0. Okay, now that we've done P, let's look at Q. Well, we can't get to Q yet because we've got to look at C, which needs to be knotted. So I'm just going to do C naught over here. You might be able to do this without the C naught and without the A naught calculation, but just to prevent errors being made, I normally sort of take one extra step. A little bit more time, but less chance of an error. So C knotted is, that's a 0, so that would be a 1. That's a 1, that would be a 0. That's a 0, that would be a 1. That's a 1, that would be a 0. That's a 0, that would be a 1. That's a 1, that would be a 0. That's a 0, that would be a 1. That's a 1, that would be a 0. Okay, so now when we look at Q, Q is equal to P or C naught. So we're looking at these two columns over here. Okay, so it's an OR gate. Remember the rule for OR gate. If any of the inputs are 1, the output is equal to 1. Okay, so keeping that in mind, we can then say that we've got C naught that's 1 over there, so that means the output of 1. Over here both are 0, so that would be an output of 0. Both are 1, so output is 1. We've got P that's a 1 over there, C that's a 1 over there. Both are 0 over here, so that gives an output of 0. We've got C naught that's a 1 over there, and both of them are 0 over there, so it gives an output of 0. Okay, now we look at the next output from a gate, which is R. Okay, so got R over there. R is Q ANDed with A. Okay, so we're going to be looking at the two outer columns, and I AND it. Now keep in mind with the AND gate, all the inputs need to be 1 for the output to be 1. So we can see over here that A's got 4 inputs over here that are equal to 0. So that can automatically tell us that the output for R would be equal to 0 for those 4 conditions. Over here, we've got A that's equal to 1. So we can basically look now at when is Q equal to 1. Well, Q is equal to 1 over here. So that would mean that both A and Q is 1. So an output of 1. Q is a 0 over here, which means that the output would be 0. Q is 1 over there, and A is 1, so the output would be 1. And over here we've got A was 1, Q is 0, so the output would be 0. Okay. Let's look at the next output. So we've got S. Okay, so S is R XORed with C. Okay, so remember with the XOR expression, if we've got 2 1s or 2 inputs that are 1s, then the output would be 0. If both inputs are 0, the output would be 0. And if it's only one input that is a 1 of those two, so one input is a 1, other input is a 0, that will give you an output of a 1. Okay, so let's have a look. We've got we've got R, and we've got C that we're going to be looking at. So C is 0, R is 0. So that means S would be equal to 0. C is 1, R is 0. So 1 XOR 0 is equal to 1. C is 0, and we've got R is 0, so S would be 0. C is 1, R is 0, so S would be 1. C is 0, R is 1, so S would be 1. C is 1, R is 0, so S would be 1. C is 0, R is 0, C is 0, R is 1, so the output would be 1. And we've got C is 1, R is 0, so the output would be 1. Okay. Alright, then finally, we've got the output Z. And the output Z is essentially A nor S. Okay, so it's going to be A and S is going to be all together, and then not it. Okay, so that's again the outer columns over here. So 0 or 0 is a 0. Not it gives you a 1. 0 or 1 is equal to a 1. Not it is equal to a 0. So essentially we can say, well, if any of the inputs are 1s, it's going to be output of 0. If both inputs are 0s, it's going to be output of 0. So we can see both our inputs are 0s over there. We've got one input over there that's a 1. We've got both inputs over here that are 1, so the output would be 0. Okay, we've got a 1 over there and a 1 over there. All together, not it will give you an output of 0. We've got A that's 1 over there, S that's 1 over there, so that would give you an output of 0. And A is 1 over there, S is 1 over there. All together gives you an output of 0. Okay, so that is our truth table. Basically looking at what the output Z would be for all the different conditions of A, B, and C, or all the different conditions for your inputs. Okay, so now it becomes a situation, now that we've done that, we've got to write the expression. And this becomes then a bit more of a challenge. Okay, so essentially, we will be able to say, well, if we look at, we'll be working from the output and work our way in. So let's have a look. So let's say we can see that Z is equal to A or S, and that's or not it. Okay. So A, we're able to leave, that's one of our inputs that we know. So we're able to leave that. But S is not one of our inputs, it's not A, B, or C. So we've got to expand S. Okay, so if you look over here, S is equal to R XOR C, or C XOR R. Okay, so we can say in this expression that's equal to A plus, so S is equal to C XOR R. Okay, and that's or not it. So essentially, whenever we've got a letter that is not one of the inputs, we will place it into a bracket and just have a normal substitution type of scenario. Okay, now C is one of the inputs, so that is acceptable. R is not one of our inputs. So what's R? Well, R is equal to A and Q. Okay, so that means we can expand this to equal to A or C XOR of A and Q. Okay, and that's or not it. Okay, A is an input, C is an input, A is an input, Q is not an input. What's Q? Well, Q is equal to P or C naught. Okay, so we can represent this as being equal to A or C XOR of A and what is Q? And we say that Q is equal to C naught or P. And that's or not it. Okay, but P is equal to, it's not one of our inputs, so P is equal to A naught and it with B, so A naught B. Okay, so we can then say this is equal to A or C XOR of A multiplied by C naught plus P, we said is equal to A naught B. And that's or not it. Okay. You will notice that we didn't go and sort of say, well, C is have over here variables after the gates knotted. There's no need for that. We know that an input knotted is equal to that knotted. Okay, so that's our final expression. Now, I'm aware that there are ways and rules of simplifying expressions, and you are able to do that. But that's something I'm not going to cover. I know that it is something that can be useful, it can be important to explore, but it depends on where you're going to be exploring and using it. For what we are covering and what the common sort of tasks we do in mechatronics, it's something that doesn't get covered that much. So I'm not going to go and explore that. But it is possible to reduce this expression with less variables. But that, like I said, is something we won't necessarily cover. Okay, so that is the answer. So we were given the diagram, we had to find a truth table, which we found, and then we found the overall expression. I wonder if you noticed the error that I made over there, specifically referring to the last column, where z is equal to a or s, not it. Okay, so let's just have a look at this again. So it's a, which is 0, or 0 is a 0, not it gives you a 1. 0 or 1 gives you a 1, not it gives you a 0. Okay, now these two rows over here specifically is where the error occurred. Okay, so 0 or 0 is a 0, not it is a 1. A 0 or a 1 is a 1, not it is a 0. And again, 1 or 1 is a 1, not it is a 0. And that's the same for all of these rows that are to follow, which are both 1s. A 1 or a 1 is a 1, not it is a 0. So just be very careful with these type of truth tables. As you can see, when one does rush it, it is possible to make an error. And yeah, look at specifically those two lines, how easily it was that I made an error unintentionally initially. But I thought to leave that error over there so that you can see how easy it is that it happens. And one just needs to be really careful when you do these truth tables. Okay, so let's have a look at another example. So now, in this example, you are given the expression, which is z is equal to a not b plus c, that's all knotted, multiplied by ac, and that's all XORed with b. Okay, so now you've got to find the logic diagram, the circuit diagram. Okay, so we've got A, B, and C. Those are our inputs. Okay, so let's look at the first term. Well, A is knotted, so I'm going to put that through a NOT gate. As a matter of fact, what I'm going to do is any of the other inputs, A, B, or C, knotted? We've got a knot over there, but that's our expression knotted. Just only A that's knotted, so I'm going to just put a NOT gate over there. Okay. A not ANDed with B. Okay, so we've got B over there, and that gets ANDed together. Okay, the next expression we've got is the output of this A not B is ORed with C. So we're going to take that output and we're going to OR it with C. Okay. Yet that whole expression is knotted. So we can make this, instead of just a normal OR gate, we can make that a NOR gate. Okay. Now the output of this expression in the first bracket, that is ANDed with A and C. So we can output this. We've got C over here. and we've got A over here. We can tap off there, bring it across. As such. Okay. Right, and that is ANDed together. Okay, so now we've got that term over there, ANDed with A, ANDed with C. Okay, now the output of that whole expression, which is in the final brackets, that gets XORed with B. Okay, so B is over here, so I can tap off from that. And our XOR gate, remember, it's a curly back over there, was a double one, and then as you would with your OR gate. And that will go to an output of Z. Okay, so with when you give an expression, you've got to find the logic diagram, break it up into smaller parts, and then start adding to it as you expand. So find the center of the expression and expand from that outwards. Okay, now that we've done that, let's have a look at the truth table. Okay, so a truth table can become quite a bit messy though, and quite big. So we've got A, and B, and C. Those are our different inputs we have. Okay. And again, we're going to be looking at all the different possibilities that A, B, and C are able to be. So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Okay. The first thing we're going to be looking at, the first term we're going to be looking at is A naught. So I'm going to have A naught over here. Okay, so A naught is, that's a 0, so that's a 1, that's a 0, that's a 1, that's a 0, that's a 1, that's a 0, that's a 1, and all of these ones will become 0. Okay, now A naught is added with B, so A naught B. Okay. So we're going to be looking at A naught, and that's ANDed with B. So both A naught and B needs to be 1 for the output to be 1. So we've got B which is 0 over there, we've got B which is 0 over there. Both A naught and B is 1 over there, so that would mean that is 1 output over there. Over there we've got the same scenario. Both inputs over there are 0, so that will give an output of 0. And same over there. We've got only one input that's a 1, so that would mean that's the output of 0. And over here the same scenario. Okay. Now we're expanding with this expression. Okay, so we're going to be looking at A naught B plus C. Okay, and that is all. Well, I'm going to do that on its own. We'll knot it in the next step. Okay, so basically we've got A naught ORed with, we've got A naught B ORed with C. So any of these inputs need to be 1 for the output to be 1. So over there both are 0, so the output would be 0. Over here we've got 1 that has got an output of 1. Over here we've got 1 that's got an output of 1. Over here we've got both inputs that are 1, so the output would be 1. Over here both inputs are 0, so the output would be 0. Got one input over there that's a 1. Over here both of them are 0, so that will give you an output of 0. And over here we've got one input that's a 1, so that would mean that the output is 1. Okay, now we're going to knot that. So it's going to be A naught B plus C, or knotted. Okay, so 0 knotted is 1, 1 knotted is 0, 1 knotted is 0, 1 knotted is 0, 0 knotted is 1, 1 knotted is 0, 0 knotted is 1, 1 knotted is 0. Right. Next expression we're looking at is A and C. Okay, so this is now essentially A and C is ANDed with that expression. So what I'm going to do is I'm just going to have A and C on its own. Look at them independently. I can do that because remember it's that expression ANDed with A ANDed with C, so I can separate them in that way. Okay, so A and C, remember both inputs need to be 1 for the output to be 1. So we've got 0 over there, 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 we've got 1 over there, we've got 0 over there, we've got 1 over there. Okay, now we can go and say, well, what is A naught B plus C or knotted ANDed with AC? Okay, so again we're going to be looking at these two columns and both inputs need to be 1 for the output to be 1. So that is 0 over there, that's a 0 over there, that's a 0 over there, that's a 0 over there, it's a 0 over there, it's a 0 over there, it's a 0 over there, and a 0 over there. So all of the output for that is equal to 0. Okay, now that we've done that, we can look at the final expression, which is essentially, I could go and I could write this expression and then say X or B, or I could just say plainly Z. That's the output. Okay, so remember, it's this column over here that's going to be XORed with B. Okay, so remember, with the XOR expression, it's like adding binary numbers. So 0 plus 0 is 0. 0 plus 0 is 0. 1 plus 0 is 1. 1 plus 0 is 1. 0 plus 0 is 0. 0 plus 0 is 0. 1 plus 0 is 1. 1 plus 0 is 1. Okay, so that is our truth table. Alright, so if you look at this, we were given the expression. From the expression, we were able to derive the schematic diagram. Again, just looking at the expression from the center, moving outwards and adding each sort of section as we go along to the diagram. And then we look at the truth table. Again, same scenario. We look at the expression, look at the smaller aspect of it, breaking up into smaller parts, and then bring it up to the final expression. Let's have a look at an example where you're given in a truth table. And you've got to find the logic circuit diagram and also the expression. So with this example, I'm going to be looking at two scenarios that you can often come across in some form of application and that you've got to solve. And the one goes into the next, as you will see. So either or is typical truth table examples that you would be given. Okay, so let's take a scenario of where you've got a car. It's one of these fancy cars. And this car has got a sonar sensor, which might be at the back of the car to tell you that if you are maybe as you're reversing, there might be some object in the way or so. Okay, so we'll call that sonar sensor A. And every time there's this buzzer inside of the car, or this little alarm inside of the car, and that's got to go off as soon as the sonar sensor is activated. Okay, this buzzer also has to go off every time the door opens, maybe. Okay, so the door opens. Okay, so door which opens is we're going to call B, but the buzzer will only go on if this door opens when the headlights are on. Okay, so that would be your headlights, which we will call in this instant to be C. Okay, what you could find is often you could find some black box. I call it a black box. It could be some unit in a vehicle or that you come across and you see, oh, it's got an output of that goes out there called, let's call it Z over there, and it's got a whole bunch of inputs. Might be, in this scenario we've got 3, but it could be more. We don't know. And so you measure the voltages for different on the output for different combinations of inputs on A, B and C, and as you do it you generate this truth table. Okay, so this truth table would now consist of, again, 3 inputs. So we've got A, B and C, and each one will consist of 8 bits or 8 different scenarios. And what we're going to be doing is we're going to, if you look at this specific example, well, let's just look at all the different combinations. So the different combinations of inputs we can have is 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay, so in this specific example, we want whenever the sonar sensors are activated, in other words, A on its own is activated, the output must be equal to 1. Okay, so if you look at A on its own over there, you will see that over there, for these 4 inputs over here, the buzzer will go off. So we can indicate that the output over there is 1 automatically. Okay, now if you want to look at when the doors are open and the headlights are on, that the buzzer must come on. So B and C, for both of those inputs, must be equal to 1 for the output to be equal to 1. If you look at this, you've got a scenario that it happens only in this case. It happens in this case. So what happens in this case? But this last option, we've got A also equal to 1. So that is a situation where either or of those options it's already telling us it's equal to 1, so we can actually just accept that as equal to 1 anyway. But we also want it to happen when, in this situation where A is not activated, so the sonar sensors are not activated or not detecting any obstacles, but the door opens while the headlights are on. So we're going to make that to 1 as well. And all the other scenarios will be equal to 0. I mean, if the doors do not open and the headlights are not on, we don't need the buzzer to go off. And so these scenarios will be all 0 over there. Okay, so now we've looked at the one way of application where you could have this scenario where there's different inputs come in and you've got to generate a truth table. Or you could have a black box and you've been measuring the different inputs and the output for that combination of inputs, and you could generate this truth table. So you're able to generate a truth table by some measurements or by given some conditions that you need to take into account. The other way that you could have is you could almost skip this, and you could have a problem where somebody comes to you and says to you, well, listen here, I've already done all these investigations and stuff, and this is the truth table I've been able to find. Please assist with generating a logic circuit diagram and the expression. And so you could also be given like just this truth table and have to work from that. So now you get to the truth table, and so you've got this truth table, and now you've got to generate an expression. So what you do is you look at this truth table and you look at all the scenarios where Z is equal to 1. So it's over there and over there and over there and over there and over there. Okay, and then what we're going to do is we're going to, every time, we're going to be looking at each row, but specifically the ones that Z is equal to 1. And we're going to take that different inputs of A, B, and C into account for the expression. Now, if it is that, I'm going to say X, this X could represent A, B, or C. If X if you find that you've got an x, and that's equal to 1, we're going to represent it just as x. But if x should be equal to 0, we're going to represent it as x naught. Okay. So if you look at this case, the first scenario we've got over here, where z is equal to 1, we've got a is equal to 0. Okay, so because a is equal to 0, it will become an a naught. Okay, so therefore our expression, we can start writing that as z is equal to a naught. But b is equal to 1 and c is equal to 1. So for that, we're just going to call it bc. Because it's equal to 1, it just stays as that specific variable. Okay, so a naught, b, c. So we're adding them all together. Okay, then we look at the next one where z is equal to 1. And so the next part of our expression will consist of an or a plus. Okay, so we look at the next one where z is equal to 1. A is equal to 1 in this specific situation, so we just write a. B is equal to 0, so we write b naught. C is equal to 0, so we write c naught. Okay, then we look at the next line, where z is equal to 1. Okay, so now the next one, a is equal to 1, so we write a. B is equal to 0, so we write b naught. And c is equal to 1, so we write c. Let's look at the next line where z is equal to 1. Well, a is equal to 1 over here. B is equal to 1, and c is equal to 0, so that becomes a c naught. And then lastly, the last line has got the z equal to 1, is where a, b, and c is equal to 1, so that will be a, b, and c. And that's your expression. Yes, I do agree, as I mentioned before, there is a way of simplifying it. This specific scenario, you probably will be able to get away with simplifying it and having only 2 terms or so, but that's not what we're going to worry about. In this specific scenario, we're able to get 2 terms quite easily, and you probably have figured it out logically by using some of the gates that you've learnt of already. But sometimes it is more complex in type of situations and scenarios where you can't necessarily just see the solution in that way. So we just having this expression in this format will be acceptable. Okay, so now we've got the expression. Okay, so we found the expression. And remember, we're either given the truth table or we're given some scenario. Both of those situations are possible. You could either be given the truth table or some scenario that you need to take into account with a black box. Okay, so now you found the expression. Now we've got to find the logic circuit diagram. And for this, we're going to be using the expression to get it. So again, we're going to have 3 inputs. In this case, we've got A, B, and C. Okay, now you'll see over here in this expression, I've got A that is A naught, I've got B that's B naught, and I've got C that's C naught. So what I'm going to do is for both of those inputs, I'm going to put that through a NOT gate. So I've got already a naught, a B naught, and a C naught. So whenever I come to those specific inputs for my from this expression, I can just tap off either from the A side or the A naught side. Okay, so we've got A naught, B, and C. So we've got A naught over there, we've got B coming into that, and we've got C coming into that, and that's all ANDed together. Alright, now let's look at the next term. We've got A, B naught, C naught. Okay, so we've got B naught and C naught over here already, as such. Now we just need A. So A we can actually maybe take over here, tap off from there, go over here, and we can have it as an input over here. And we put that through an AND gate. Alright, let's look at the next term. So now we've got A, B naught, C. Okay, so we've got A A, B naught, C. So B naught we've got over there. We've got A over here. And we need C. C's over here. You can see C coming up over there. So we can tap off from that and come down over here. And these all get ANDed together. The next term, A, B, C naught. Okay, well, we've got A over here, which we can tap off from. We've got C naught, which is over here, which we can tap off from. Now we need still B, and B is over here. So we're going to bring B down as such. And this will also go through an AND gate. Right, and then lastly, if we look at our final term, we've got A, B, and C. Okay, so let's have a look. We've got A over here, A coming down over there, so we can tap off from that. We've got B, which is indicated over here, coming down, so we can just tap off from here and come down this way. And C, C, we don't have a way of, we haven't tapped off from C yet, have we? We have over there, but have we? And over there. So let's just bring it down over here. Okay. And that comes also over here. And that goes also through an AND gate. Okay, now we're going to have a big OR gate. Okay, now all of these terms that were ANDed together that we've done over here is getting ORed together with the plus signs. So the outputs of all these AND gates are going to be fed into this OR gate over here. Okay, so this one comes out and we can bring it down over there. This one we can bring down in over there. This one we can jump over there and bring it in over there. This one we can bring across as such, and this one can come in like that. And then finally that gives an output of Z. So that is a logic circuit diagram that you would then generate from this. So as you can see, we've looked at 3 different scenarios that you can come across. You can either be given a circuit diagram and you've got to try and find the expression in the truth table, or you can be given an expression and you've got to find the logic diagram and the truth table, or you can be given a truth table or some scenario such as this that you've got to, or some application, and then you've got to find the expression, and from that you're able to get the logic circuit diagram. So with this, you're able to have the fundamentals of how these logic systems are working and how to use them. As you've seen, a lot of them apply to the binary sort of addition and expressions that we've come across and worked with over there. Yes, there are more gates available. There are more logic system configurations, latches, and things that are available, but that's a little bit more advanced and things that I don't think is really needed for the basic understanding of your mechatronic system. It's something you can always explore later on.